stuff. Okay, so it's an icebox problem. Question number 2 is a stoichiometry problem. If you remember your stoichiometry. Question number 3, or I guess letter C, is 2-part. Pay attention to the information. You've got temperature, you've got volume, and you've got moles. I'm asking for pressure. The question you got to answer is, how do you figure out pressure if you're given temperature, volume, and moles? Do you remember?
Isn't it the KP?
Not that one, it's the gas law. dV equals nRT, okay? And then if you've got 3 different gases in the mix, and you want the total pressure, what do you use to get that? Not the average. Remember Dalton's law of partial pressures? Total pressures is sum of the pressures of the individual gases. Okay. And then if you look at the second one down, the hydrogen sulfide question. Part B is another icebox. And then part D is partial pressure. So you're back to your ideal gas law. And then part E is manipulating equilibrium constant. So you got a few things that are on this. I just wanted you to take a few minutes. This is not intended to be, it's not a quiz. You should consult notes, you should consult your neighbor, talk about it. Or you can work solo, it's entirely up to you. But take a few minutes, see what you think. Okay. And then I will cover some answers. If you get stuck, you should ask.
These ones? Yeah, I did them wrong. So,
Okay, cool.
I was thinking.
I see what you're using. You know, this should work.
What are you looking at?
That should work, what you're doing. You're doing this Kc equals.
Yeah, and then I said that H2O is 0.1, But I feel like that's an initial concentration, like so what I'm trying to calculate is the final concentration, so it's saying
And
that's
these are
final
both still
zero.
unknowns.
Yeah. So that's why I'm like,
Is there something else that uses the temperature?
well, so the one that we need to convert like Kc to Kp, but I don't think that we do.
We did a thing going to KP, but I don't think that.
That's what we
We have KC, we have RT, and we have the number of moles. That would give us KP. But
And then I know that like concentration of CO has to equal the concentration of H2, right? Because it's essentially squaring the same number by the end of it, since they start off with the same amount. I think.
oh,
Basically, like
no, of course. So here at the beginning, those are 0.
right.
So
Yes.
then we
Oh, I
can
forgot about the
then we can
X
do that.
thing.
We'll get using the quadratic equation, going for x.
Okay.
I was like, I don't know what these are.
I know, right? Okay.
I'm like,
and then
those
we
are
know-
just 0, 0.
Mhm.
And then,
And that
so
means
this
this has
is
to go down by 2x, right? Whatever x is.
x equals,
And
is
that
that
one
what it
should be
is?
minus 2x, right? Because it has to go down twice as much as
No.
base gain.
No, because there's no coefficient, so it's still just 1.
Okay.
Because that's what it is right here.
But doesn't want the 0.
If there was 2
Oh,
moles
right,
of
right,
H2O,
okay.
then there'd be 2
Right,
in
because
front
if
of
it went
it.
to completion, then these would end up being 0.100 as well. But since it doesn't go to completion, we have to use Kc. If that makes sense. You're right. I just had to think
I'm
of
just
it.
gonna like nod.
Yeah. I just had to like think of it in my.
I'm like, I'm not sure where KC goes in yet, but
Right. Okay, so then we have 0.00 minus x. And so these are just plus x, right?
right? Because we have x and x, and this is equal to that one. Is it?
Yeah. That sounds right.
And then we are gonna subtract it over to here. No. But
So then that'll be 3x,
Hold on.
right?
is it 2x or is it x times x?
I think it's x plus x because when you add them together, they have to equal the other side. I think we can also try and see what it comes up with, and then see if the number makes sense. Because however much this goes down by should be the amount that those go up by, and if we don't do that right, then it won't come out right.
So here I have it where the 2x's became x squared on this one.
And that was one of the examples he did in class.
There are some problems where we start out with problems not.
Which is then where you end up having to use a quadratic equation.
Okay.
I feel
yes,
that
I
it
think it is x
follows-
squared. Okay.
Which then makes it negative
will just be X and that will be X.
Okay, so I got 0.2.
You don't put it in the expression. Yeah.
Right, it has to be X squared because if you look at when you multiply the concentrations, yeah. And then do we need to do anything with KC? Like after we.
So, KC, you just math, you look at that. So,
We need to find the quotient constant
so I write this
on
math.
the reaction quotient.
And then I x times x.
Oh, right.
Solve it. So this is split it into quadratic.
Initial line. Calculate the reaction. And the direct.
So we just forgot to multiply the
Yeah. You gotta increase KC.
Now we can determine the reaction quotient yet.
Okay, so before we turn it into a quadratic, let me draw it out like show you how he had it set up. Where's all this?
I was like, my answers aren't making sense.
Yeah. I know, I was like, it's 0.2.
I don't know. That honestly has no
And I knew it couldn't be of a negative because then it would be a
I
negative.
got 2 negatives, which I'm like, well, that's not right.
Yeah. Okay. So.
But I'm far from the pro using my calculator, so.
Oh, sweet.
So I'm like, I might just not be putting it in right.
Right. Okay, so he said that we have to set these up so that they look like that. So we've got KC, which is 0.6 is equal to, and then if we've got, this is CO and this is H2, then we get x squared over 0 minus x.
So it's products of a reactant.
Yeah, exactly. And then you rearrange to the quadratic.
Because then we're getting that other number in there.
Yeah, I know. I was like, how do you separate it? I don't know.
I was like, well, I guess it equals 0 at the end.
Yeah. So yeah, does that like make sense? I also skipped some steps, but like, so I multiply both sides by that, and so you'd end up getting 0.016 minus 0.16x.
Yeah.
And then I moved it all to the other side, so then it ends up being plus 0.16x.
Okay. I was moving the other way.
Oh right.
And I'm
Well,
just like-
and that should give you the same number.
Yeah, but I was
anyways.
dividing by x2 instead of subtracting x.
Oh no.
I was like, I'm still have a fraction.
Yeah.
This is not right.
are stuck on the first problem, letter A. Ah, okay. So let me.
We look at it.
So let me go to. You're stuck on the first one, letter A. Go this much.
Let's try this again.
Actually, a lot of the headache.
I still feel bad.
Okay, so the first thing I'd say is that you're never wrong if you build an icebox for any equilibrium problems. You may not always need the entire ice
I don't
box
have
or
it,
ice
but this
table
is
in order
right.
to solve the problem, but it's never a bad idea to build
Still think that's
it.
not right either.
Next, anything that's a solid or a liquid you don't include in any of the calculations. You don't, they're not involved. Then, you should be able to, at this point, write this thing, which is concentration of water times concentration of CO. Not CO2. Concentration of CO divided by the concentration. Well, I didn't butcher that whole thing. At least I got my numbers are right this time. Okay. You should be able to write the K expression. Okay. And then you should, it tells you here equals 0.16. So the first thing to understand is that when you take these equilibrium concentration numbers and you plug them into here and do that math, that's the result. Okay. Then, in the initial row, unless otherwise specified, your products are going to be zeros. Just fill that in. Okay. And then you read down a little further, and it's nice, it gives you a 1 liter vessel, and it gives you 0.1 moles of water. Your concentration here is 0.100 moles. You get 0.1 divided by 1, 0.1. Okay. Any questions at this point, just this point? All right, then, if you start at zeros, you can't get any smaller. So these two have to add. You got to increase, go up. The H2O has to go down, so there's a subtraction. But you don't know how much. You don't even have any concentration values here in equilibrium. So this goes down by some amount X and then up by some amount X for both of those. Okay. At equilibrium, then, you've got okay. Any questions to right there? All right, Curtis. Molarity. Usually for these, you want to calculate them in molarity. These KC numbers, this is always going to be in moles divided by moles or pressure divided by pressure. Or excuse me, molarity divided by molarity, pressure divided by pressure. So you want to make sure that these are molarity. Okay. Plug all this stuff in. So you get 0.16 equals x squared, x times x divided by, okay. So x and x, go up here, x and x. And then this is on the bottom, 1, 0, 1, 0. Okay. So substitute like this, and then am I okay to just do x squared plus 0.16 x minus? To rearrange it like that? Did I lose anybody with that thing? Yes? Okay. Just multiply this and then subtract quadratic format. Then, if you've got a solver, These things are great. So I put in second order. So I put in those numbers. Solve. One of your answers is most likely going to be negative on these, and you'll notice that. But you can't go from 0 to negative concentration. The only solution that works is the second one, so 0.0697. That means here, 0.697 molar.
So how would we do this if we don't have a solver? Do we just plug it into the quadratic?
You got the quadratic memorized?
Yes.
Yeah, you got to plug it in there. So you've got the, like what do you have, 83? 84? Mine's built in. I've got this button right there. Which doesn't have that. I don't. This is not an 84. This is. So either, I'd say two things. YouTube's your friend. If you don't have the program for the quadratic formula, go to YouTube. Program quadratic into 84. Find a buddy who's got it copied.
Yeah. Right, like I've been using this for like 9 years. Like I don't know how the handles will choose. Right. Yeah. Right.
All right. What questions do you have on that problem? That's just part A. So I know that like I can write these numbers and pick up them in blue. It goes up by 0.0697, up by 0.0697, down 0.697, because it's a 1 to 1 ratio. So then 0.1 minus that gives me. So at equilibrium, concentration, you write this, concentration of H2O concentration of CO, and then the concentration of H2. So that's A. Do you have questions? Any confusions on this problem? Even if you're like, I don't quite know what to ask, you have something sitting there, you can stumble through it, stumble through the question, I can. Yes, Marissa.
So I don't have my calculator on my calculator. I don't know if I'll be able to download it, and it's been over a year since I've done quadratic.
Okay.
So can you refresh my memory on how to do that? Because I haven't done it.
Is that right?
Yes.
Okay.
And then it just goes back.
Fair warning, that was like 400 years. Might as well be 400 years ago.
You got a
But,
calculator the problem solver.
Yeah. So, Marissa, like seriously, if you go to YouTube, because there's got to be somebody who's written the program that you can just say, okay, here's how you do it. That'd be my suggestion, honestly.
I just don't know if I'm gonna have something like up and running and working for sure.
Do your best. Memorize this thing. See what you can come up with. I mean, that's.
You could put it on the. You could put it.
I
on one of our
could,
equations
if
as
I
well.
could remember to do that. So.
Or you can do like multiple choice questions.
You should go on the multiple choice questions. All right. Any other questions about part A?
I just have a question.
Yeah.
On the ACS, are we allowed to use graphing calculators or just a regular calculator?
I'm assuming because we have to make graphs.
I think probably if you were to I don't know, I need to check on that. I don't have a problem with graphing calculators. I mean, if you were to take the time to try to program in all the stuff in here, kudos to you, you probably never use it. The time involved in doing that is sufficient for me. So I don't have a problem with that. Like, unless I'm told otherwise, I'm gonna say they're fine.
Okay, cool.
Okay. How about part B? Would you have a clue on how to do part B?
I didn't even look at part B.
It's not too bad. It took
So
me
if
a
you've done
second.
part B,
Talking
how would
about
you do it?
grams?
What's that?
Moles, I think.
You're talking about moles?
So in part B, I want to know for the equation here, how many, you can put it, I want the answer grams, it says just minimum amount, but I want grams. What's the minimum number of grams of carbon that you need in order to get equilibrium? Okay. Take a look at the concentration of carbon dioxide. Or carbon monoxide rather. What's the source of the carbon in carbon monoxide? Carbon. Okay. So I know for this one that my concentration of carbon monoxide is how many moles per liter. I know that it's in a 1.00 liter container. That tells me moles of carbon monoxide. And then there's 1 carbon per 1 carbon monoxide. What do you do at that point? If I'm after mass,
So you find the mass.
mass of carbon, which is
Multiplied by-
the periodic table, 12.01 grams of carbon to 1 mole of carbon. Please notice, labels all over the place. Moles disappear, and your answer is in grams of carbon, whatever that number works out to be. It's like,
0.837.
in other words, and remember, solids are not included in your equilibrium expressions. So as long as you have a minimum amount of carbon, like that much carbon in the container, you'll hit equilibrium. That's the minimum. You could have more than that, it doesn't change the equilibrium, but that's the minimum. Questions about that? Makes sense. Okay. All right. How about part C?
I'm a little confused on that one.
Okay. So let's do
Pressure
this.
times volume equals moles
Um,
times the constant times temperature.
Are you good with that? The volume times molarity is moles. This is how you're going to deal with part C. And the volume of the container is 1 liter. So if I've got a concentration of 0.0697 moles per liter of hydrogen, that I've got that many moles of hydrogen. Okay. And I've got 0.0697 moles of carbon monoxide, and I've got 0.0303 moles of water. Okay. Is that okay? Any questions about that? Here's why you need to know it, and then I'll take it back as
Okay.
You're using the idea of gas law, PV equals nRT, and you're after the pressure part, which is N times R times T divided by V. Okay. And if you look at the information that you've got, moles here, all the way across, R is a constant, 0.08206. Temperature is given to you at 800 C, so temperature equals 1273 kelvins. And the volume of the container you have is 1 liter. So you can figure out the pressure of each gas. You go pressure of H2, 0.0697 and then back over here.
I got 0.930 moles for H2O. Because isn't it 0.1 minus?
Long math.
Actually, no, I think. No, because that adds up to 0.1. No, you're good.
Shouldn't the temperature be 1073?
1073. Yeah, it should be. I can math. And then temperature 1073.15 kelvins. And all of that's over 1.00 liters. So the pressure of H2, and realize the pressure of H2 and carbon monoxide is the same because you got the same number of moles, same volume, same temperature. Pressure of CO equals, anybody have that answer?
6.13.
Okay. And then you need to do it one more time to figure out the water. I'm just going to write R. Rose, if you have that one.
0.0153. I think.
I got 2.67. All right, and then the last part, Dalton's law.
Is it 0.3 something?
0.0303.
0.30.
And then you just need to add those up.
You just add it.
And then we got three significant figures, so we'll report 2.9. Okay, back.
So since everything's held constant, why can't we just add up the moles and then multiply R and temperature and then divide it? Like, why shouldn't that work too?
Yeah, you'll get the same thing.
It
Okay.
should.
Okay. I just want to make sure before I.
The letter D down here.
Right. Okay, that makes sense.
So part of, I mean, you're right. You can, for this one, you can go total number of moles and you should get the exact same answer. Part of it is to say, oh, Dalton's
Just
law part
remember.
pressures, and then when you go down to your part, question 2, part D, that is a Dalton's law. You gotta isolate just the S2.
Okay.
Okay. Liz, you have a question? Didn't give you the total pressure. So you got the temperature up here, you got the KC number, you got moles, and you got volume. So there's no pressure. And then part C, where you've got numbers of moles, and you've got the temperature and the volume, that's where I'm asking you a question. Any other questions about the first problem? All right. Say that again. With this part? Yeah. Yeah, so on this calculator, so I've got this solver program built in, second order, and all I need to do for this thing is type in the 1 from there, the 0.16, and then the negative 0.016, and then I hit solve. And it gives me the two, those are the two solutions you get with quadratic, right? And then you're looking at which one is reasonable. If you start with 0, you can't add a negative number to it. You can't have less concentration than you start with. So so the only solution that works is the 0.06966, so you round that up 0.0697. That's what I have here for S. So 0 plus that, equilibrium concentration. This is 1 to 1, so it's the same thing. And then it's decreasing by the same amount because it's 1's all the way across. Subtract 0.1 minus that number gives you that. But that's the way my solver works. And then and like I said, if you don't have it, figure out how to program it. Can't be that tough. Especially with DT. Right, Marissa? Because you got hours of spare time. Because we all have hours of spare time. Anybody try question 2 yet? Okay. So, I'll tell you what. This is what I'd like you to do. I'm actually not going to give you the answer for me. On your paper, I would make an ice box. And here's my question. What do you do with that 3.72 times 10 to the negative 2 moles of S2 at equilibrium? Where does that go?
Bottom right.
What about here? 3.7. That way. You know?
It's right on the bottom.
Right there. Okay. But it's in a 1.25 liter container. So you've got to do, I'll give you a little bit of help here, 3.72 times 10 to the negative 2, and a 1.25 liter container. There's your concentration. And then my other question before I say go is, what do you do with a 3.40 gram sample of H2S? Where's that going to go?
Convert it to moles.
Convert it to moles.
And then molar.
Molarity, where's it go in the chart?
Top left.
Top left, right there. Okay. I'm going to freeze that. Okay. See what you can do like next 10 minutes to solve this. That's your answer to the concentration. Well, you can figure it out, but pretty good. But I have no idea.
alpha again, and it gives me, if I press solve again, it gives me the pressures.
I don't have an answer to that. That's kind of nice.
So you can just click back and forth. You can solve and solve. I'm a genius.
But I guess
then.
I don't know what it is that it's.
I don't know what it's doing.
Why it's giving, I mean, it's cool it's giving you the numbers, but I don't know what the math is. It's a calculator to do that for me.
Can I just do it this way now?
If you trust that it will work every time.
I don't, but that's okay.
We'll try it again.
Let's try it with a different one.
Yeah, I'm not a. Kind of bother. Okay, once you get part C, if you get part C, go ahead and skip D and jump down to part E. I want to see what you can do with part E. So,
I think it's like 32 So when we're finding the concentration, do we do 2 of this divided by the liters?
Yeah.
I think you just need to know that it's a 4 gram sample.
Do we want to find the concentration?
yes.
Yeah, so you do,
Yeah, H2.
and then that would be moles by, divided by the 126.
Do I multiply it by 2? So we multiply that.
2 moles of that should equal 2.4.
It should be 2.
And
For-
if I multiply the molar mass of
For
H2S by
molarity.
2,
No.
I don't.
Because you account
The
for
grams
because when you do
per
your
liter.
X's, you'll account for that there. So yeah.
So grams to moles, and then over the 1.25 liter.
Yeah.
Well, you gotta double.
Becca, you could get 27.3 for the molarity of the H2S. Now what do you get?
For the molarity of the H2S, I got 0.0798.
Did you divide molar mass by liters?
I did, no, so I multiplied 3.40, or I divided 3.40 by, I think it was like 38 or something.
I totally forgot.
Okay.
Okay, so the mole of S2 gas at equilibrium, what part of this question does that come in at?
The molarity. How did I do equilibrium?
Not moles at equilibrium of S2.
So did you get 0.997?
0.798 or 0.0798.
Okay, you divided 3.4 by 27.267. Oh wait.
No, sulfur I think was like 32.
Okay.
So is that actually that should be the concentration?
So since it's moles, first you have to divide it by the volume. So you have to divide that number by 1.25, and then that
That
gives
is
us
similar. But then which part of this question do we end up using it on?
It ends up being this one for KC.
Okay.
Because you have to
Because
calculate.
I was looking at what's up there right now. It's like, I
Like,
don't
what do
think that we need it. Yeah.
And actually, it ends up being making it much easier to find H2 and the equilibrium equations for H2, because then you know that X is equal to that. Because if it starts at 0 and it's plus X, then X is equal to 0.029. So it's much easier than using a quadratic equation.
Okay. Explain to me what you just said.
Yes. Okay, so when I was setting up my icebox, so we know that we're starting off, so first we have to calculate, because we start off with 3.40 grams of the H2S, and then I converted that to molarity, and then we know that everything else is starting out at 0. And then once we move on to down here, we know that there's only one S2, so we say plus S, and then there's 2 H2, so plus 2X, and then 2 H2S is minus 2X. And since we calculated this, we have a full equation for this. So we can say that X is equal to 0.0298.
And this was calculated where?
Yes, using this. And that's the one that he has up there.
Okay, so we use that to get here. How?
So if you take, so we
My
have
brain is
moles.
catching up with the words.
Okay, you're good. So we've got moles, and we want molarity.
Yeah.
So if we take this number and divide it by the 1.25, that's what we get.
Okay, because this is the amount present at equilibrium.
Yes, exactly.
Is that concentration? So, okay, that makes more sense.
Right.
I was like, nodding, but I don't. I just don't see where it goes.
And then once you do that, then you can, since we can say that's equal to X, then we can multiply it by 2 and get that, and then use that same number and then subtract 2X from that.
Okay, awesome. I'm gonna reference your paper.
Oh yeah, you're fine. Well, I'm just doing other things, so. I double checked with him, so it's all right. Because I was like, I just want to make sure these are good, because otherwise I'm gonna want to recalculate them.
Wait, are the other ones right? My God. We did it.
And then he said we
Oh
could
my
skip
God.
D too.
Okay.
Yes. That makes me so happy. 0.02.
And then he actually routed it to force committee members when he did it.
Wait, didn't I just do that?
But he said that might not be close enough, but when I carry it through, it has to make it a little bit different.
So you told us to skip C and go to D.
Yep.
Go to C, skip D. So we just find KC.
Yes, because now we have everything.
So we go to H2, 0.05952 squared times 0.0296 divided by 0.0203 trick. This was on the test, and I feel like it's a trick. Instead of first. That's what I thought, but I think that was wrong. I expected that in the teacher. What are you thinking I have?
Yeah, so
Wow.
you're rounding, yeah, keep 3 digits. So keep 3 non-zero, so.
Mr. Davis?
Yeah, that's good. And then when you skip, if you want to go for D, I mean, you can skip around. Show you up here. Holly, you can.
No, I'm not there yet.
I've been helping.
So you got that one. That's good. Is this you? Oh, this is back.
That's her.
Okay.
Hers are good,
Rosalie.
mine's not good yet.
I feel like I got this wrong on the test, and I just don't want to be annoying here. So
I use, this is using that equation.
No, so this one is pulled directly from that, 'cause it's just asking for the equilibrium concentration of these guys.
Okay. So this is actually as simple as this plus this equals 0?
Yes. I know, it doesn't seem like it, but if you think about it, like...
So this is negative 0.0297?
Oh, the x's.
Yeah.
Yes. Yep.
Okay.
And that's what he got too, so...
No.
Are we gonna get to... Are we...
I'll give you a break.
Are we gonna get to the Chateliers principle?
Yeah, we do the Chateliers
Chat.
all right, so on this particular problem, then I'll take a break and then answer whatever questions are at that point. I wanted to, some of the math on this thing. In walking around, most of you are in the right direction. But here you go. So my icebox looks like that, and this is the one. I put this one up for you, right? So you've got the concentration is in moles per liter. You've got 3.72 times 10⁻² divided by 1.5 gives you that number. That's your x value. And remember that this goes up by x. And I saw a lot of you had the next one over here that's up by 2x, and then a lot of you had this one down by 2x. That's what you need to understand about the way the icebox works, okay? Is that once you identify, for example, in this case, that thing in equilibrium, and you know the stoichiometry 2, 2, and 1, that change row lets you figure out the rest of it. So, 0.02976 up by 2x, that means you double it and you get this number. This one has to go down by 2x because 2.1. Okay, so down negative 0.05952, up positive 0.0592, and then here. Then you do the math. This row for the equilibrium row, that's the addition, and then that's the subtraction. So at equilibrium, you have these three concentrations. Any questions to that point? Okay. Then, let's see what I've got. I think the next row is asking for KC, right? On the next problem. So asked to solve for the KC, you are using your equilibrium values. You plug in your numbers. There they are. This is your S2, the H2, and the H2S. And you should square the two of them. And if you do the math properly, you should end up with that. Okay. Questions on the K? No units. All your K's are unitless. Okay. So all K's are unitless. The other thing I really want to stress, y'all, and I don't see too much of this, but just to, like, don't do that. Seriously, if it's 0.02976 on your calculator, keep at least 3 digits. So, no, I would say at least 0.0298. If you're going to do any rounding, keep at least 3 digits out there. Okay, but if you just start chopping numbers and arbitrarily rounding, your answers will not match mine. And they won't be all that close in a lot of cases. So don't arbitrarily round. Okay? Fair warning on that one. Then, the next part was, oh, that was for the concentration up at the top. The one thing I do see people do, and I saw this a couple times, people think you got 2 here, so that means you got to double things in here. The only reason this 2 and the 2 are up here is to balance the equation. There is no impact on calculating moles. Leave that alone. It's like, don't even think about it being here. Okay? Don't double. Doubling bad. And then finally down for part E, I said go ahead and skip D. If you did D, great, I don't have an answer for it. I haven't solved it yet. But for part E, hopefully you're recognizing that the reaction is written in reverse, number one. And then number two, the coefficients are all cut in half. So the math on it means that you're gonna square root the inverse. And if you square root the inverse, you're gonna get 1.97. Still no units. All right. What question is going to answer about problem 2, aside from letter D? Tom. So that's this thing right here. 3.4. I saw that a different number there for a couple of people, but you do need to remember that it's in 1.25 liters. And the other question I had was, don't you need to solve that first before you do the math by liter? And sure you can, but you end up taking that answer and dividing it by 1.25 anyway. So mathematically, when you take a look at, put the unit on here, the units cancel grams, and you've got moles on top, liters on bottom. That gives you molarity, which is right there. Any other questions about this? Ariana?
Is it one part E how everything is reversed and cut out what it looks like reverse and double?
Then you square it. Yeah, so if you'd say K, C in the reverse, which will be equal to you double it and then square it.
So,
Yeah, perfect.
what if it's like a fourth of it?
Right, so the fourth power, 1/4 power. So you cube, whatever, quadruple root it, fourth root, whatever. Quadruple root.
Quadruple.
Yeah, fourth root. Megan, you had your hand up here. Yeah. Anything else? Confusions? You'll see an icebox on Thursday. So I want, questions answered. I figured it'd be worth going through at least a couple of these. Okay.
I think it was thoroughly helpful.
I'm not a total monster. Okay, freeze that. You want to take a I don't know, 5 minutes or so? Come back and finish out the Chinese principle and talk about something.